So this is a explanation of the geospatial encoder that's in NuPIC currently. And this is more in depth on how the encoder works, how it achieves its properties, and how it works inside of the Hound demo that we recently released, which is the anomaly detection for GPS movements. So we'll start with some basics. First, what is an encoder? This will be useful for people who are not familiar with this. An encoder is, it takes raw sensory input and it produces a binary activation of neurons. So the brain is operating on just electrical activity. It's just doing pattern recognition on neuronal activity, but it has to somehow interface with the real world, right? So the encoder takes the real world input and translates it into something that the brain can understand. Or in our case, something that the CLA can do pattern recognition on. So some examples of encoders are, these are the biological equivalent of encoders. In the vision sense would be the retina, which takes light and translates it into electrical activity of neurons. Cochlea in sound translates, sound waves into electrical activity, and the geospatial encoder takes GPS readings, translates it. And each of these would basically produce a binary array of neuron activations with the following property. The important property of encoders are that semantically similar inputs translate into overlapping bits in the output representations. And I'll explain that a little bit more. But really, the reason that property exists is to speed up the learning for the CLA. So it can generalize between semantically similar inputs easily. This is just a property speed up learning. Okay. So what are the properties for a geospatial encoder? Imagine that you're trying to create a geospatial encoder and you have a series of GPS coordinates. What properties should the encoder representations have for a set of GPS coordinates? The first one is that, remember that semantic similarity in the GPS case is spatially similar, as in points that are close together. They're semantically similar, so they should translate into output bits that overlap. So positionally, spatially close together should have overlapping bits in the encoded representations. That's the first important one. The second important one is when you consider that people are moving at different speeds, what's close together changes depending on your speed, right? So if you're moving at low speeds, then the encoder should consider the resolution of movement, should consider very fine resolution of movement. It should be looking at very sort of high resolution. And when you're moving at high speeds, the resolution should be more coarse. And if you go to the next slide, you'll see that, here's an example. If you're walking, moving from here to here isn't that big of a difference. They're 20 feet apart. The encoding should sort of overlap in the bits. But if you're moving from here to here and you're 200 feet apart, that's pretty different when you're walking. Those are different positions. So the encoded representations should be very different. They should not have overlapping bits. But if you're driving, then the same 200 feet apart that used to be different in walking is now pretty close. So you haven't moved that much on the highway. But 2,000 feet apart, if you move farther along, then that's different in driving. And again, it's different if you're flying. So really, your speed determines what semantic similarity means. So the encoder should respect that. That's the second property. Those are the two main important properties of the geospatial encoder. So now we'll get into how it actually works and how it achieves these two properties. So the first step is to initialize the encoder. And the way it does this is, so you start by dividing up the space. So you have the Earth or whatever space you're trying to encode in. You divide it up into a grid of little squares. Okay. Then you assign each square a random value between 0 and 1. And each square is going to have a different value. It's going to be a floating point value, so it's each square is going to have a different value between 0 and 1. And this is fixed for that square. It's deterministic for that square. And the value, this is the square's order. All All right, and we'll come back to where that's used later. Then you map each square. So each square gets a value from 0 to 1. It also gets a mapping to one of the bits in the output. So you have your set of bits in the output. A number of them can be on, most of them will be off in the typical sense. But each square is going to be mapped randomly to one of the outputs. Now remember, there could be a lot of squares and fixed number of bits in the output, so you can have multiple squares mapping to the same bit in the output. That's not an issue.
Question. Dividing up this space, when you say this space in like a Cartesian coordinate system, does that mean the entire space?
Yes.
Okay.
So if you're trying to map the Earth, you map it onto a 2D space, and then you divide that up into little squares. So there's a little caveat to this. This is actually just a virtual step. We don't actually do this. If you go to but I'll explain that in a second. If you go to the next slide. Here's a sort of visualization of that initialization process. So you've divided up the space, as a map, into squares. Each square gets a value. So here's 4 example squares, but all the squares will get values. These 4 examples, they have random values between 0 and 1. It doesn't matter as long as they're random, they're fixed to the square, and they're floating point value. And also each square gets mapped to one of the bits in output. So if this is the output vector, and remember that our encoder is supposed to make these bits either 1 or 0, on or off, then this square corresponds to that bit, and this square corresponds to that bit, and it's random. And again, it's random, but it's fixed, so that square always maps to that value.
You mean each of those random values maps to one of the bits?
They're independent. The value is the square's order, and also the square has a corresponding bit in the output. And they're used in different ways. So they don't really have, they're not tied together. They just are fixed for that square. Okay, next slide please. So this is some notes on the initialization process. The size of the square is a parameter to the encoder. So you might have asked how big should those squares be? And that's a parameter, it's called scale. And the smaller the scale, the smaller the size of the squares, which means you'll have more squares. And I'll explain what that parameter does later on. The order is that value from 0 to 1. It's a way to deterministically order the squares relative to each other. So if you have a set of squares that you're considering, you can order them by that value. And we'll use that later. And then note that, so this, when I mentioned that initialization process is virtual, what that means is we don't actually go through and give every square a value. We actually use a deterministic uniform hash function so that we can, given a square, we can get a random value. Given the same square, we always get the same random value. And we can generate these values as needed. Right? So when you have a set of squares you want to consider, then you can generate these values using the hash function and do whatever operations you want to do.
So it's not necessarily random. It's a hash function. It's a hash value.
Yes, it's a hash value. But it's random in the sense that there's no real meaning for a square doesn't get a particular value because it has some relation to anything else.
Well, the real definition is a hash value, not a random value.
Yeah, but the squares there should be no there should be no relation between the values like adjacent squares or faraway squares. They should all just be, in that sense, it's random. But it is a deterministic hash function. The reason we need a deterministic hash function is so that the same square will always get the same values. Right? And this is an optimization that allows us to scale to infinite spaces. And you'll see more details on that later. All right? So the initialization process is kind of, I use it to explain to you what's going on, but we don't actually do anything. All the work actually gets done when you try to generate an encoding. All right, next slide. So how do you generate an encoding? This is where the meat of the work happens. So given an input in this case is a GPS reading, which contains the latitude, longitude, and speed, we want to produce an output, which is a binary vector. And the way you do this is, first you find the square in the grid that this GPS position corresponds to. So you do this using a map projection. So you project the Earth onto a 2D map using some sort of form of map projection. We're using the same map projection as Google Maps. And then that projection on 2D space, you have a location that you're trying to encode. You find the square that location falls in, and then you draw a box around that square with a certain radius. Okay. Then you choose the top W squares that are contained in the box, and W is the number of bits you want active in the target number of bits you want active in the output. Right. So if you have 2,000 bits vector, and you want 40 of them to be active, then you draw a box around the square and you pick the top 40 squares. And you activate the corresponding bits for those squares. For those winner squares, the ones that have the highest order, those squares get their bits activated. And then at the end of it, you have a binary vector with 40 active bits, corresponding to the top 40 squares. All right. If you go to the next slide, here's an example. So let's say that's the position you're trying to encode. That's your current position. So first we have to map use a map projection to figure out where that point translates in a 2D plane, and then using your grid, you find the corresponding square. That's this one. You draw a box around it, and then you pick. Let's say you want. In this example, we have. I don't know how many bits those are, but I think maybe 40. And we want 5 of them to be active. Then, and with the geospatial encoder, you want a low number to be active. You want it to be sparse, so that collisions aren't as much of a problem. And we can talk about that more later. But you take so if you want 5 bits to be active, you pick the top 5 squares by order. And the top 5 squares, in this case, are these ones. And all the other ones have lower order. And so those top 5 squares are picked as winners, and the corresponding bits that they map to, those are activated in the output. And that's how you have your encoding. So are there any questions so far?
How did you come up with the radius?
How do you come with the radius? Great question. Next slide, please. It's almost like we prepared that. How do you come up with this? Oh man, all right. One more slide. So note that this satisfies property number 1, which was that the positions that are spatially close together should have overlapping bits in the output. So if you go back 2 slides, you'll see that this position generates this box, right? But if you had this position instead, then you would have this box, which overlaps a lot with this one. So if you pick the top 5 squares, you would be very likely to pick, so you wouldn't pick that one because the box would not include it, but you're likely to pick these ones. And maybe one from here. So if the boxes are overlapping, you're likely to pick the same bits, same squares to be active, which means the same bits active in the SDR. So similar positions have overlapping boxes, which translates into overlapping representations, encoded representations, right? Okay, so 2 more. Now, what about property number 2 though? Property 2 was to consider the resolution of movement as the resolution of movement should be more fine when you're moving at low speeds and more coarse when you're moving at high speeds, right? So how do we satisfy that? To answer Lewis's question, next slide, we modify the encoding process with this slight change, which is that, or it's not even a change, it's just a clarification. The radius that we pick for the box is proportional to the speed. All right, so everything else is the same, but the radius is determined by the speed. And so the way, the bigger the speed, the bigger the radius of the box. Next slide. So how it'll work in this example is, if you had a low speed, you draw a small box around the position. If you're going at high speed, the same position, you have a bigger box, which means you're considering more of the squares as part of your encoding, right? More squares that are candidates. So note that if you were to move one square over at low speeds, the 2 boxes would overlap, but not by that much. Versus if you were to move over one in high speed, when you're moving high speed, the boxes would overlap by a lot more, right? The percentages of squares that overlap is higher in the case where you're moving at high speeds, which means that the same movement in the two cases is going to translate to more similar representations in this case than in that case. So if you're moving at higher speeds, then the same amount of movement is going to have more overlap in the output, binary output vector. So this satisfies property number 2. And hopefully that's convincing. Okay, so if you go back 2 slides, there's one more. One more consideration is another question you guys could have asked is how do you, so the square size that we talked about earlier, how you determine that is that parameter called scale. So note that if you make it the parameter smaller, if you make scale smaller, the number of squares will be higher and each square will be smaller, which means you'll be able to encode, the maximum resolution of your encoder will be higher. So if you'll notice that every position is going to fall into a particular square, and every other position that also falls into that square is going to end up having an identical representation in the SDR. So the square is some size, and there are many possible positions in that square. Each of those positions is going to have the same representation, right, by our encoding. So the size of the square, it reflects the maximum resolution of the encoder. So by reducing the scale parameter, you increase the maximum resolution. Now remember, the actual resolution can be determined by the speed, but the maximum resolution is going to be determined by the scale. And so if you set that lower, then you'll have a higher maximum resolution. But also it means the encoder will have to do more work per encoding, because it has to look at more squares per encoding, because there's more squares in general. So it'll take longer to run.
Does that also mean, like, as a repercussion within NuPIC, that like a smaller scale or higher resolution encoder means that it's going to catch smaller level patterns as well, and maybe miss the very large patterns?
It shouldn't miss the larger patterns, because
Like these bits, I guess.
yeah, you'll just have more bits of squares available to represent stuff, but if you're moving faster and you have the bigger movements, there's still going to be the resolution. The actual resolution is actually still going to be determined by the speed. But if you increase the scale or the resolution, sorry, by reducing the scale, then it can catch the smaller movements that it couldn't have caught before. So if you have too big of a scale and you walk around, it might not be able to tell the difference between you walking from here to there versus you walking from here to there, because it looks the same to the encoder.
So the only downside to having a small scale is speed?
Yes.
That's it?
Yes. Ideally, if you had like, an infinitesimally small scale, it would still work just as well, and in fact, it should work better. But it would just take much longer to run.
Is it possible to dynamically switch back and forth? So let's say you have something that's going very, very fast and then very slow. Is it possible to change the square size and the number of squares that you're involving in the area of focus?
Typically, you wouldn't change the square size. You would set it to your desired maximum resolution. And then as you change your speed, it'll automatically change the size of the box and therefore change the resolution of encoding.
And you can do that pretty fast and on the fly.
Yeah, it does that for every value that it's encoding. For each value, it determines the speed, the size of the box based on the speed. So every change to your speed is going to translate to a change in the resolution.
The size of your radius, W, that you put in is directly related to the size of the scale, right? So if you've got a much finer grained scale, you've got to have a bigger radius to be able to catch the overlap, especially at higher rates of speed, or is it unrelated?
So does it propagate through that function?
I think only if you have variance, slope variance between those scales. If you have like go from 5 kilometers walking to driving, I don't think that would make a difference in the size of that.
So
Only if you have a very pretty.
Is radius the number of boxes, or is it a fixed distance? Is I guess the real question.
Radius is the size of the box.
The radius is the size of the box that you use for the encoder. Scale is the size of each square. So if your radius is 5 boxes and your scale is really small, you're going to be picking up a very small area. So how do you, at higher speeds, you're gonna go get out of that.
Yeah, I think the radius is probably not in terms of the number of squares, but in terms of physical distance.
It's
Based on the speed.
Yeah, it's
It's
Okay.
very dependent.
Yeah, that's what I was trying to do.
Or
Thank you.
W would be like if you go very slow, slowly accelerating.
Yeah.
I think that's what happens with W.
Okay.
And also, regardless of the size of the box, even if you have a lot of squares to look at, you still have a target number of final bits that you want active in the output. So you're gonna still take a fixed number of squares, the top
Okay.
W squares. So
I was confusing radius and W.
Yeah.
Two separate variables, sorry.
yeah, the radius is determined dynamically by the encoder. The scale is the parameter that you use.
Yeah, okay, gotcha.
Okay. 1, 2. Okay, so one more. This is the demo. So as you're moving along, this is at walking speeds. Each of these pixels represents one of the squares, and the white ones are active. As you move faster, you'll see the number of squares that are being considered. The box is getting bigger, and notice adjacent positions have similar bits. A similar square, it's the same squares overlapping that are active, which translates into overlapping output binary vectors. And as you slow down here, the box size becomes smaller. So it's doing that for every single value, for every single reading, it's choosing the size of the box. So it changes dynamically based on your speed. And this is visualization of the actual encoder working.
So it looks, the encodings look denser at small speeds, at lower speeds.
That's only because the box is small, but if you were to count the number of bits, so this is just the squares, right?
Yeah.
In reality, there's a binary vector that's fixed size, and as many white squares as you see are, those many bits are active
Okay.
in the binary vector.
Oh, I see.
So if you count the number of bits, you'll see that they're always almost exactly the same.
So the sparsity going into the CLA is always constant.
Yes.
Mm.
It could slightly change because you could have, actually no, since you always pick the top W, it will always be W bits that are active.
You could have.
Couldn't there be-
Oh, but there could, two of those picked ones could translate into one
Yeah.
bit, so you have fewer than the active. That's what I was trying to remember that. So it could vary,
That's
but it's
very
very
rare.
unlikely to vary. So the sparsity should be pretty fixed coming out of the encoder. Okay, so up to this point is the geospatial part of the encoder. Are there any questions so far?
Yeah, I have a high-level question that may not be obvious to people listening
Okay.
here is, this is a very complex scheme, and the question is, why did we need to go to such a complex scheme? You could imagine like a very simple, similar to what we do with scalar encoders. Let's say you did X, Y, and speed as a three-dimensional space, and then just did a normal scalar encoding, where there's none of this randomization, and you just have a ball that's moving around. What's wrong with that? Why did we have to go to this? It might be worth explaining those.
Yeah, that's a good question. So if we were to just use the X, Y, and speed as scalar values, then each encoding is going to look
Similar things still have a lot of overlap, so you still have that property.
that's true. But the second property with the speed changing the resolution of the encoding,
No, that would also, speed is another dimension, so it's a 3D space that you're encoding as so as you change speed, you also have overlapping bits.
let's see.
So the problem with that is that we need a fixed size
Yeah.
vector.
It's the same
And
reason
Same problem with the scalar encoder, you have to determine the min and max ahead of time, and the resolution, which we don't have to
so
worry
this
about yet.
allows you to build an encoder that works over essentially an infinite space
Yeah.
without knowing the boundaries, without saying where is zero, and not knowing the extent of what you're going to encode.
Yeah, and that's even more clear in the next slide, or the slide after this one. So the coordinate encoder is a generalization of these ideas, and it shows you some of the advantages of doing it this way. It's pretty powerful compared to just encoding them each value as a scalar value. So it's a generalization of the ideas, and it's, in fact, the geospatial coordinate encoder is a subclass of the coordinate encoder. That's how it's implemented in NuPIC. So instead of taking latitude, longitude, and speed, it just takes coordinates and radius. And coordinates can be, it determines the position that you're encoding, and it can be in any number of dimensions. So you can have like, it doesn't have to be 2 dimensions, as it is with the geospatial encoder. It could be 10 or anything, right? And the radius determines the radius of the box that we draw. And in a higher dimensional space, it would be a hypercube, or however you call it. Would not be, so the box is just for the 2D space. But, so this is more general, and it allows you, and it also translates to infinite space, right? Because we're using the hash function to only look at the squares within the box. You don't have to know the size of the space beforehand. You can have infinite space as long as you can translate a particular coordinate. As long as you can get a particular coordinate for your problem, and you pick a radius, depending on your speed or any other factor, you can get those two properties that originally talked about. So the next slide, the advantages are that you can use infinite space of any number of dimensions. Its runtime is in the number of squares. It's linear in the number of squares that the box contains. So, and that's determined by the scale and also the number of dimensions and all these things. But it's still linear even in a infinite space, considering the other variables. And another really cool thing about it is, so we talked about scalar encoder just now. If you actually set the number of dimensions to 1, and the coordinate is just one value, that's a scalar value, then you can set the radius dynamically based on the past statistics of the data. So if the values are changing really rapidly, you can set the radius to be higher. If they're changing slowly, you set it to be lower. Then now you have a scalar encoder with dynamic resolution, which is something we don't have with the RDSE, because we had to pick the bucket size and things beforehand.
Dynamic resolution meaning as the speed of variation within the scalar value as it streams in,
As it changes, the resolution of the encoder also changes. So this is, I guess it's kind of like a generalization of the scalar encoder idea. And it's best applied to the geospatial case. So
The problem with that is if you change the radius based on the statistics of the data, the more the radius changes, then the more your previous learning gets out of whack, right? So you generally don't want to change that radius as you're going. I mean, you don't want to change it based like, oh, the last 1,000 data points says it should be this radius, the next 1,000 data, because then your learning will be screwed up too, right? You can't change that stuff and expect all your previous temporal memory to be still good. Am I right about that?
well, the temporal memory is learning for that particular resolution. It's learning the sequences
For a particular radius.
for a particular
But if you
radius.
change the radius, and your prior learning will be kind of messed up.
Well, you'll be learning. The prior learning will still be there for that particular
Radius.
scale, right? For that particular
Yes, but
radius.
if you're changing a radius based on recent statistics of the data, and so now I'm going through the similar sequence with a different radius because the statistics change.
But if your radius also encoded,
Was that?
if you encode the radius as part of the.
Yeah, it depends how fast you're changing this. If you change this really fast, when you go back into that old range, you could go back into that old radius. And then
Yeah, that's what I was trying to say.
The old learning
If the
is
data
so-
is kind
Well,
of,
but
You're
here's,
changing it every time step.
I'm just reacting to the fact that you're saying it's based on past statistics, and if that's constantly changing, and your radius is constantly changing, then your memory is going to be based on the radius. It's going to be tied to that radius.
I guess it also depends on the patterns of the data. I was imagining a data set where you typically have some patterns in a low scale, like in the 1 to 10 range, and then you also have patterns in the 100 to 1,000 scale. So when the data like gets into that scale, then it's gonna still remember
Yeah.
the data
Yeah.
learning for that scale.
Yeah, but if the radius is dynamic based on not just where you are on the scale, but just statistics of the data, well, there's a lot of finesse to this, but if you change the radius and you go through the exact same sequence, your memory won't be.
Yeah, there's some conditions here where it could get into a lot of trouble.
Yeah.
So
Okay,
they're,
Yeah, but I think it's, what's nice result about this is that it basically goes back to the old scale, similar to this, the current scale encoder with the same property of no min and max.
yeah. And another thing to note is that even if you have different radius, if you have similar positions but different radiuses, the representations are still going to overlap some amount.
Somewhere.
Right? They're not going to be totally different just because you change the radius, and it'll differ by the amount by which you change the radius.
Yeah.
So it's very like continuous
Yeah.
and nice like that. Okay, I don't know if I have a nice. Oh, wait, resources. So if you want to learn more about the encoders, the geospatial encoder, there's a link there. The coordinate encoder, this is the code, and it should be pretty easy to read in the way it's laid out. And then the geospatial anomaly demo is there, and the encoder is what powers the geospatial anomaly demo. So you might have seen this before in previous office hours, for people watching. But it's the demo basically can take routes, it can take movements and learn the patterns. It uses the geospatial encoder to create the encodings, and then the CLA to learn the sequences and generate anomaly scores. So the first time you monitor the route, it's all red because nothing has been seen before. It's all anomalous. Red is anomalous, green is normal. And then second time it starts making predictions, so more things are normal, more things are green. Fourth time around, it's learned the route. And note that each of these times, every position is going to be slightly different because of variations in traffic, because the sampling rate, but it's still able to learn the general sequence because of the properties that we talked about with the encoder. And it's also able to identify traffic anomalies and spatial and temporal anomalies. And if you want to learn more about that, there's we have, I think, another video for the geospatial anomaly demo, and more coming.
What are some of the parameters that dictate how fast that training set is going to be? In other words, here it takes about 4 times till you get a really great prediction output, and I imagine sometimes it would take 3 times, sometimes it would take 10 times. What are some of the parameters that you would keep in mind when guessing how long that training set would be?
Well, the possible factors I can think of are what the data actually looks like, how fast it's changing, how much variation there is in the patterns, what the maximum scale of the encoder is. If you set it too high, then walking speeds, we've seen that as an issue. Walking speeds, it's not able to really learn the sequences, so you have to set the right scale. But the cool thing is you just have to really only set that parameter, so it's not like you have to tweak the encoder too much. The learning rate of the CLA is another factor. You can speed up learning by changing how many the temporal memory parameters. But other than that, like it was nice because when working on the geospatial anomaly demo, I found that it really worked pretty well out of the box, and it learned pretty quickly, even with real world data. So, and the encoder is kind of designed to do that anyway, is to really be dynamic to the changing data, and as is the CLA. So, not too many parameters. Really, I can think of those. Maybe you guys can think of some other factors.
Do you want to mention just what a good size and W would be for it?
Okay, so I think if you went to that link, you'll see the model parameters for this demo. I think it's in 4,000. The output of the encoder is 4,000 bits, and 52 of them are active. I might be making that up, but you can check out the actual numbers in the encoder. So W would be something like, you want it to be pretty sparse, something like 2 to 4% of the available bits. And the scale is, I think, 5 meters. So each square in the grid represents 5 meters of space in the real world.
With given the resolution of GPS, it doesn't make sense to get it narrower than that.
That's true.
It was 30 feet.
Yeah, it could, even if the movement is bigger than 5 meters, it'll still use the whole radius dynamic resolution thing. So it's okay if you have too small of a.
Yeah, it's not going to mean anything.
But yeah, there's a
The
trade-off
GPS
there
resolution
between
is 30
speed
feet,
and.
then getting your pixels smaller doesn't really mean anything because you're just not going to be that accurate.
So with those numbers, how many random spots on the Earth can you have until you start getting confused?
That's a good question.
Did you do
I think Scott did that.
That's supposed to be like a lob.
What's the answer? Scott did some nice analysis on
You can
this.
answer it.
I mean, you can do it as like the whole Earth in like inch by inch, and you'd have to feed way more records through the CLI than you could process in your lifetime for it to actually hit a collision. There'll be overlap, but not significant.
So what's the slowest it would take, or longest number of paths through a desired space versus fewest number of paths? Like what's the domain that you'd be looking at for really good data in the training set?
That's a different question, I think. isn't it?
Yeah.
Okay.
Yeah, sorry, I kind of went slightly to the side. Oh, okay, so, do you see what I'm saying, or no?
How many paths through a
Yeah,
typical
so
data
like-
set do you need to learn the
Or even a
route?
non-typical, so if you were looking for like the absolute worst training set, that you could imagine and still get any kind of result versus the absolute best. I
But we
imagine
usually
you'd
don't
have to do
repeat
it.
a data set. We just usually just stream data in, and so you go repeat a path multiple times, but it's just one
Yeah.
path.
yeah,
Here's
yeah.
something- here's something we saw
I mean,
with- Here's something that's really nice about Grok, which should apply here as well, which is if you have highly repeatable data sets, meaning, if this path was exact same path and exact same speed, you could learn it in one step. If you're learning it fine, you could detect very small, subtle changes to it. But what if someone did random walks through this territory all the time?
Yeah.
And what we found is even data that looks very, very random, very unpredictable, has a predictable component to it. It's just not obvious unless you actually encode in randomness. It's really hard. And so we look at data sets, metrics coming off the servers, they're like, wow, this is unpredictable. But it turns out Grok can make some level of prediction for it. And the way that the anomaly detection works is it may take a bit more data, but it'll eventually be able to say, this thing is statistically different. So that would be an interesting experiment, is to, something, I don't know how you even do it, just sort of meander around on a field or something and going place to place, and then have someone else do it who has a different mentality and see if you can detect the difference. It might be surprised. So it could be very, very non-repeatable looking data, but there's still some structure to it that's sometimes hard to see.
Yeah, basically the question is how do you make it break, and how soon would it break? Like what is the absolute, if you push it to the limit in terms of giving it just terrible, unpredictable terrain, what's the limit beyond which it wouldn't really be able to do predictions?
I'm trying to answer that
Yeah,
in the sense that what happens is to detect an anomaly, it will take a much longer amount of data before it says this is an anomaly. So it doesn't break in an absolute sense. It degrades, and it takes longer and longer and more data to say, hey, statistically I can show that this has changed. So one data step, one small deviation along the path and do nothing, a whole bunch of do nothing, and then after a whole bunch of them, and say after like a minute or 2 minutes of watching this thing, it says, well, you know what, I think it's unusual. So it doesn't have a limit, it's just sort of, it grades,
Yeah.
it takes more and more data to discover the structure and anomalies in very, very noisy data patterns.
So I think here you're not feeding in time of day right now. Right? Is that right?
I'm not,
In
yeah.
the model parameters. So with those model parameters, it wouldn't be able to pick up time of day related patterns.
Oh.
So let's say you typically do this path in the morning commute, and now you suddenly did it in the middle of the afternoon, that same commute. It wouldn't treat that as an anomaly because it
For
doesn't.
this
have time of
particular
day.
demo.
But that's easy to solve. You could put in the time of day encoder.
Well, it actually might pick it up as an anomaly if you do it in the afternoon because there'd be less traffic you over.
Okay.
The assumption is that
Okay, if there's something else
you're
that's
doing a non-standard time.
Yeah. If there's some other thing that's different, then it'll pick that up,
Yeah.
but not the time of day.
But there are problems where the time of day matters, and there's problems where the time of day doesn't matter. If you were tracking, maybe something like flights of an airplane between two major cities, and maybe they fly all day, all night long, and then the time of day doesn't really matter. But it's hard to say.
So that's questions?
No, we have no questions.
Okay.
If you guys would allow me to wax philosophical for a moment, I think this is really interesting. I've been playing around with this for a while now, and and working on the geospatial demo application. And if you think about this is an interesting sense, this geospatial encoding thing, that it would have been great if we had evolved with this over the past several million years. And certain people have a good sense of position on the earth and direction for some reason or another, and I'm not sure we totally understand why. But there's also migratory birds and insects that seem to know exactly where they're going all around the planet. So this is not a new thing. It represents itself in biology, it seems, and we don't totally understand how it works. So I think this is really interesting that we can do something like this with NuPIC and see it sort of working. It's really awesome.
It could get even wilder than that if you.
Yeah,
So people can learn new senses. Mm-hmm. So if you imagine that you created a GPS encoder that actually fed in encoded data into your brain somehow, could even be touch or on your tongue or something like that, cochlea or vision, and actually translated GPS coordinates into an encoder that had various properties. You could learn a new sense, which is.
DARPA would be really
perfect.
So I actually worked on a project like that. You guys remember I worked on the thing for the blind?
Yeah.
But anyway, another philosophical bent is something actually when in the end chapters on intelligence, I wrote about where machine intelligence is going to go, and I said one of the most interesting places it will go is in new senses, because you can build a cortex, you can build them smaller and bigger and faster and slower, but the really interesting stuff is going to happen when people start figuring out how to encode other information that we just can't actually access at all, and I had no idea what that would be, but we're starting to see some really interesting ones. This is a very, the whole idea, the way we did this infinite encoding is pretty cool. Then now the geospatial thing, we've got the cortical I/O word encoders, but I think there's going to be more. And so I think a big part of machine intelligence is going to be doing weird senses that pick up strange stuff. Maybe you could do protein folding sense. And so now I have a system that actually understands protein folding, because we can take protein folding metrics and turn them into the proper SDR.
The stock market sense.
Well, that was a little bit more mundane. But I mean, I really think about, think how hard we think about mathematical concepts and physics concepts. We struggle as trying to understand things that do not map well to our time and space coordinates. And now we can come up with a sense that just intuitively senses those things amazing. When you were talking here, I was imagining the bubble chambers in particle accelerators. And how would you build an encoder for a bubble chamber and a particle accelerator to actually sense particle movements, if you don't know what bubble chambers are. But that's another cool thing, because there's tons and tons of data that people are trying to figure out what the tracks of these particles and bubble chambers. So there's a whole bunch of cool stuff we can do. This is the beginning of an era of amazing senses.